Alright, so right here I just wrapped the string around this particular pin one time for some added friction. And then I just threaded it through this tension spring, a little piece of spring that I sewed into the side of the bone. You can see that's the side of the spring. I just threaded it through between a couple of the coils, and that adds a pretty significant amount of tension to this pulley here. You can see the string runs all the way through, wraps around that, and then runs through the spring and then comes down. It's got about 3 feet of total distance, and that will need to feed into this pulley. As I pull on this pulley, it's going to transfer all the string. It's going to winch in this pulley while releasing this pulley. This pulley, which is acting as the flexion muscle, which is the main one we're testing, it's currently fully flexed, so it's fully wrapped up. And we're currently passing it across. You can see the little line right here, the line right there, going across to this big pulley. It's now filling up this big pulley on the right. It's going to be winding, adding to this side. So this is this side mainly empty. I made it that big without any string on it. Just by wrapping it in a bunch of string and then wrapping that in glue. So that's like the default size of the pulley. To get the mechanical advantage, it has to be a very large diameter pulley relative to the size of this diameter of the inside of this pulley. And then here, this smaller, thinner section, that's going to be our transfer point to transfer to the pulley that's going to ultimately be right here next to it. So this is the smaller one, that's the bigger one. The bigger one. So if you go from small to big to small, you just got mechanical advantage gain. And this will be like, I'm thinking like 2.7 to 1 or something like that on average. But it changes, the mechanical advantage changes over time as the relative diameters of these change as the winding occurs. So it's not a consistent or fixed mechanical advantage. So it's going to range from like maybe, it looks like it's probably like 1.5 to 1 right now, but it bumps up to about 3 to 1 when it's fully wound up, maybe even 3.2 to 1 or something. So anyways, as promised, check this out. I just taped off one end of 28 gauge wire, tinned copper bus wire. I taped it onto the motor here temporarily, and then I fed the string through it. I just wound up the wire into a circle here. You can see it's it just came up, over, down, made a loop, and then came down again. It's not wanting to focus at the moment. There you go, you can see it. So I just made that by hand with a little bit of wire. And then the other side I just taped down onto this decking here. That piece of tape you can see right there. All that black tape. And so that's keeping this string that goes to this bottom pulley here. It's keeping it in perfect alignment with this bottom set of pulleys. So we're not going to get it derailing. Yesterday I didn't have this thing, and this would sometimes slip off there and start wrapping around the axle. It'd come off the section between two discs, and it would actually be winding up down here. So this is a guidance assistant, making sure it's well aligned. The string then after it goes through that guidance system, which perfectly aligns it. I don't know if you can see the string itself. Yeah, you can see it right there. There it goes, right across. It then feeds through this. Does it? Oh, it's not anymore. Well, it used to feed through. It used to feed through this spring. Pay attention. I can feed it through there again. I sewed the spring to there. It came out. Somehow unwound itself. But we still have tension being fed onto here because I taped it to a bolt. So this bolt provides a nice amount of tension to the whole system. This string is the final output of the system currently. So the final output tensions the entire system. No matter how many pulleys we had here, it would tension them all. If the output string is under tension, everything's under tension. And so anyways, I can now continue my testing. As I pull on this string, which goes to, oh, what the heck? Okay, as I pull to this string, which goes to the top pulley up here, that top pulley right there, the very topmost screw, that will unwind it and turn the entire motor shaft clockwise in the process, because it's wound counterclockwise. And as the motor turns clockwise, it's going to release the bottommost pulley right there where my fingernail is. It will release that, and that would act as a relaxation of the flexion portion of the motor system, which would cause the index finger to relax itself, no longer be flexed. Now, currently, we don't even have any extension pulley set up on here at all. I'm just testing pulley 1, which is right here, pulley 1 of flexion, as well as the main flexion pulley here. These three big discs with the 2 pulleys they make are only being used to manually rotate the motor shaft, as opposed to rotating it electronically, in order to not work with electronics right now, because I don't want to open up that Pandora's box. When all I want to do right now is just test this pulley system. I'm going to test one pulley at a time. So this one, then this one, then this one, then this one, then the one in the back right corner. We'll make each pulley, test each pulley, perfect each pulley, so that everything's being thoroughly tested as we go. And then once I've tested all the flexion pulleys and I've gotten my desired mechanical advantage, and I've verified it, maybe do a load test and everything, and do several iterations, like back and forth, to see how it holds up, or is it going to break easily. Once we verify a lot of things through our testing, then I will remove these 2 top pulleys and install the extension setup. Although I have been considering just skipping extension, but I think that would be reckless and a mistake. So I should just do extension as well. A lot of roboticists will skip extension, and they'll just have springs do the extension. So they won't have motor actuated extension at all. They'll just have springs. Like, okay, so they'll have motors do this, but when the motor relaxes, the spring just lifts it up as the motor's relaxing. The spring does all the back set of muscles for the fingers, because they feel this doesn't need to be that strong. It doesn't need to be that strong. But I thought, that's taking shortcuts. And what if it did need to be strong? What if you wanted it to, like, I don't know, flick something really fast? Now, that a spring could probably do that. Well, you guys tell me. One downside to it is when you're doing flexion, it's fighting that spring. So you're already just losing the total amount of strength to some degree by however strong that spring is. So that's a downside. I don't know. It is tempting to just skip that, but I feel like I would regret it. I'm sure there are things that we do where you want this. Do you guys ever use, like, your extension muscles of your finger in a way that requires strength? I guess, like, itching. Like, when I scratch, I might push hard to scratch up, and the spring would just be like chilling. It wouldn't have enough oomph to do that. So maybe that would be one. Or, like, what if you're digging through some nails in a bucket of nails, and you're doing this, and you're like physically moving them out of the way to dig your finger in? You wouldn't be able to do that. The spring wouldn't be able to do that with any type of load on it. It would just kind of chill. So you'd only be able to do this, but you couldn't forcefully go back up. That could be a problem. So there's, like, really weird niche cases where you really do need those muscles. And the last thing I want is to gimp my robot right off the bat, just for the sake of what? Just saving a little bit of time. It just seems like not prudent. So right now, the system's under great tension, and I'm just wanting to do this test live so you guys can see, because I believe this is going to be a really good test. So far, it's been really good. So you're getting to see history in the making. If I can pull off Pulley based downgearing, it's game over, boys. Let me put it closer to the camera, although you won't be able to see the bolt dropping. You will be able to see I am admittedly going slow, but that's because I'm trying to just study the system and observe carefully. The instant the bolt landed on my lap, the tension was relieved from the system, and I almost saw total failure occur. That fast. The system must be under tension at all times, non-negotiable. Very important. So, how do I guess to reload it, I mean, I know. Uh, okay, I got an idea. Let me just tape with some really temporary, easy to remove tape this string to the bolt up higher now. In fact, we could wind it up. This bolt is just a temporary means of providing that tension to the system. In the final robot, the tension will be provided by a spring mechanism that will pull on the string. But we're just testing the first pulley of the system, so we don't want to create whole mechanisms unnecessarily at this phase. Okay, let's continue the test. I know the dangers of lack of tension on the system. It's super important to have tension. Okay, there we go. And let's see how much we pulled out of here. I want to measure it just to make sure everything looks good. Not that front. That's not. Maybe 24.5 inches. It's supposed to be 27 inches. Maybe we can come a little more. I'm not sure. I don't know why it stopped working for a second. Alright, so I'm just helping turn it with my hand. I didn't want to force anything. It looked like it was done right. Guess not. Yeah, we're getting plenty of extra inches now. That was a false alarm. Okay, now we can measure again. It should be way, way better now. Yeah, that's about 27 inches, so it's perfect. Okay, so that's a successful test. I guess we're going to want to test the other direction now, but before I do that, I need to place this topmost string under tension. So I need a little piece of spring to run it through. And I'll also want to create a little guide eye. Just like the one we pointed out here, little eye we made right here, little metal eye with the 28 gauge wire. I want to create a little guide for this top pulley so that I have that assistance to make sure it's lined up perfectly. So that was my little test. I just wanted to share that with you guys because that's a pretty big deal, and that was a successful test. And so we've got to make some improvements to the system before we can test the reverse direction, which will be flexion. And then if that passes that test, maybe I'll start running the test faster and faster, like kind of yanking it more like a lawnmower cord, rather than just like really slow watching everything. And I'll see if that causes failures by going faster. One potential failure will be this bolt that's hanging is going to land on my stomach and stop providing the tension. That happened just now. So that's something to be mindful of. But yeah, we'll just test this a bunch of times, going faster and faster, making sure, just iteration after iteration, each time building our confidence, observing everything, seeing if anything messes up. And then eventually I will move on to making the next pulley, and that will down gear it a little bit more. And I'm going to want to also measure the output after this pulley to see like how much did it give us in terms of mechanical advantage? Because if we're winding the first pulley 27 inches, and this is supposed to be like 2.5 to 1 mechanical advantage, then the total travel of this final string here with the bolt attached to it should have only been close to half, if not significantly less than half 27. So it should have been like maybe 12 inches of total movement. Wait, can I test that? Well, I would have to observe what height the bolt was at when it started. So I don't know if I can test that. But that would be something to look into, just kind of to verify everything. This is like real hands-on experience here, so I'm excited about it. Right now we're going to be doing the reverse test of the system. Now we're doing flexion. This tape immediately came off. I'm so annoyed with it. Music is supposed to know. Okay, let's hold it there. Okay. A little bit. Hold it. Right. Everything's solid. You see the bolt is right here. So the bottom of the bolt lines up with the bottom of the cam. That will be important when we want to measure how far this bolt travels down when we go the reverse direction. We're going to measure that this time. We got 27 inches on the intake on the motor that happens. And I want to know how much downgearing this first pulley is really doing. In other words, is it going to be 12 inches or what? Like how much does it bump that 27 inches down when it's done? That would be really interesting to see. So now we use the other side and we get the motor going the other way. Uh-oh. What's going on? What was jammed? What? Why isn't this winding? Wait, what? Oh, this pin slid way over. It was actually jamming this wheel. which put a brake on the wheel. So the wheel was not under tension, the wheel was being loosened. It wasn't even bearing the weight of the bolt anymore. So this spring, or this eye, is loose. We need it pulled that way. It can't bind against the wheel. So I'm going to tie it off to the thumbtack to the left of it. So I'm glad we were able to determine why everything was failing. Because I was going slow enough, I saw that this thing had slid in out of position. You guys can see that right now to verify, with your own eyes what I'm talking about. All right, you see the metal eye right here? It's sliding into and blocking this pulley from being able to turn. You can see it's loose and it's just sliding that way and it's putting on brakes. Once this pulley stops turning freely and is on brake mode, but this one's still unwinding string from this pulley at the tip of my finger, then this is unwinding. Well, this is not winding, then that unwinding is just creating a rat's nest. It's just creating string that's just going to get tangled up in something. So that's disastrous. There has to be tension on the system at all times. So there cannot be something constricting the pulleys from turning. They have to turn freely. And this would actually argue that, like, we would even want more tension on the system than what we have, theoretically, although perhaps not. Because of something breaking it, putting on brakes, not breaking like destroying, but breaking is in slowing to a halt. Something slowing to a halt, the pulley, I don't think will typically happen. But you never know. It's a dangerous thing to think about. Alright, so we should be good to go. Top views. What is that? I catch that. Wait, what? Okay, the bolt is now back on my lap. Just gotta line it back up. Something bound up the system again. This time I don't know what that was. So that's a very, very bad sign. There was something that prevented the tension from going through. And it led to a failure. And a tingle. Caught it before it got real bad, but it shouldn't have happened. Something is wrong. Something's amiss. Okay, right now, this one's not under tension. Why is that? Oh, maybe the bolt's landing on my stomach again. Okay. Hold on. Oh, that's wrong. Wait. Yeah, that's wrong. Wait. Why is it coming back up again? Did we go too far? I'm not getting as much tension because this eye has dropped lower. It's sliding out of the tape. And that's causing the weight of the bolt not to all be going into tension anymore. Maybe we should do this. Alright, so we can now change directions. We overshot last time. Let me measure. It's supposed to go to the bottom of this thing. Let's see how much distance it moved. Okay. Should be around, measured from here to here, 13 inches. 13 inches. And the other one was 27 raw inches. So 27 minus 13 is 17, 16, 54. 14 inches were deleted out of 27. 29 divided by 2 is 14.5. We're at 27. So so it should be like 13.5. So it's a little over 2 to 1. Slightly over 2 to 1, not much. But that's good to know. It's like 2.2 to 1. Let me see. 27 divided by 2.2. Is that... That's 12.27. 27 divided by 2.1 is 12.5. 27 divided by 2 is 13.5. 2.05 is 13.17. So it's 2.07 about. Mechanical advantage gained by the first pulley. I thought it was going to be a lot more than that. I thought it was like 3 to 1, but this accounts for the fact that a lot of the time it's not providing that much mechanical advantage, only near the end. Whoa. You gotta pull on here. But not like that. You need to be up higher. Looks fine for now, I guess. Alright, so he needs to be up higher fighting. Attention to the system is very, very important. Okay, take it off. 14 inches is what we're left with, down from 27. So that's a lot more manageable. Like if we were to do an Archimedes style pulley off that, it would be 7 inches long, either way. It's still a little bit much. Yeah, it's still a lot. If we cut it down to another half, let's say it were like closer to 7, it'd be 3.5 inches either way. Now that's doable. I have mixed feelings. I kind of want to do Archimedes and do this. What do you guys think about that? But if I just do all this kind, it would be way more compact though. Archimedes, like, is not as compact. Which one's harder to set up? It's a tough call. I mean, they're both kind of hard to set up. So I'm not sure. Alright, so we're on the top one, which pertains to what? That pertains to release? No, which pertains to flexion. Flexing it again. going faster than I ever have. Probably. That was fast, guys, wasn't it? And no problems on that fast pass. If anything, my main problems right now all point to this little eye constantly moving around and not being consistent or reliable for us. It's a flimsy little thing that's trying to do a lot of stuff for us right now. It's performing vital functions. Okay. Madame? Can you? Excuse me. I wonder how long this is. This one's supposed to be 27 inches. Let me see how much it is. 12. 4, 5, 26. 26 and a half. That's just about there. Okay. Well, these tests are getting faster, and that last up and down was without any issues. It seems like once we fixed and secured that eye with the Q-tip, oh, the Q-tip's gone. It fell out. This eye is so active. Nothing stays put. Uh-oh. Oh, the screw was hooked on here, which kept it from putting tension. In that short time, we already got tangling started. Just from that. That's crazy. The bolt head was just momentarily not placing tension on the system. Sorry. House. These are toys. I mean, it's pretty. Oh, nobody's just here. Nothing else. Just events. I frustrated too. I mean, it's working pretty good. Should I do like a really fast one or something? Wow, that looks so cool. It's going fast. I mean, I guess that's what bobbins do. Bobbins go fast. Hey. Oh my goodness. I thought if it goes fast it'd mess up more, but it looks smooth and just nice going fast. I thought if you go fast, like it's gonna screw up for sure, but no. I went significantly fast, more than I felt comfortable doing. And went great. Let's try another fast one. We're just doing passes now. Victory laps, basically. Oh, something screwed up. Oh, oh no. I don't know what happened. My guess is that the tension came off the system. Okay. Okay. Uh-oh. The bolt got caught on something and immediately just got out of alignment, out of whack, tangling. Lack of tension. Alright boys, I'm gonna clean up now. So peace out. I got to do a successful test. I'd say today was a win, besides like total fluke weird accident where the bolt caught on something, the tension was momentarily relieved, and I'm going at a high speed now with my test. So that means my reaction time to noticing the issue was delayed because I'm moving my hand so fast. I'm not able to respond immediately to an issue by stopping what I'm doing. Uh-oh, hit the emergency stop button. So instead, I kept pulling for a significant amount of distance, allowing loose string to just build up. And that wrapped into all kinds of stuff and ultimately formed a tangle. And the tangle was extremely difficult to get undone and even required me to remove this whole pulley set. But this pulley set should be impossible to move because these pulleys are in the way, kind of locking them in the way. And these pulleys being in the way are a temporary thing. They were just put there for this testing so I don't have to mess with the electronics of the motor. They won't normally be in the way. Normally we'd be able to access, pull something off, and do the fix without anything in the way when we have the motor actually working. So, but I realized like I could not get anything going. I couldn't get it fixed, so I just brute force removed it and crossed my fingers, and it turned out to it managed to get out by just bending the heck out of the pulley so much that it snapped one of them. And now everything's cockeyed and stuff. It's no longer very pretty looking, but it should still work, but it took a lot of damage. So, I don't know. I mean, it's still, that'll be a good thing to test too. Does it still work with cockeyed pulleys that are kind of bent out of shape? Because I imagine that's something we will face in the future. If, like, the arm took a big impact or something. It could crack one of these pulleys or whatever. Now, what I'm thinking is maybe we could create some metal standoffs, like a cage kind of around everything to protect all pulleys, because these pulleys are delicate and prone to failure if anything goes wrong, especially if the motor's moving at relatively high speeds. And so, man, it was totally quiet. You guys, I didn't hear anything. They're silent. So, I mean, and these are the highest speed ones. After you 2 to 1, the next one's 4 to 1, the next one's 8 to 1. Each one will be moving slower than the one before, because the mechanical advantage trades speed for torque. So as you get into higher and higher torques, you're getting into lower speeds and higher torques. So these are the highest speed ones. As I add more, there'll be lower speeds involved. You know, it is extremely tempting, honestly, to just maybe mount like one direction onto the motor, the other direction just put on the forearm, just to keep them out of the way of each other, maybe. I mean, although there could be room, but we've got room in the forearm too. Oh man, it's tough to say. I mean, if you put them both on the motor, I mean, it's still theoretically possible. There's room for it. I'm just thinking like, oh man, if anything goes wrong, it's a mess. But I guess as long as you can remove the top group, carefully remove them all, you'll be able to fix the bottom group and then put the top group back on. You have to have quite the surgical procedure to do all that. It almost makes sense to me that I would just have like a bunch of motors with pulley and maybe electronics made, like just mass produce them, quote unquote, not really mass production, but relatively speaking for a DIYer, I'd make a bunch of them. So we'd have backups. So if anything happened with the tangle or whatever, we would remove the entire motor and just disassemble everything and just rebuild it. But that could be done at our leisure, whenever. It would just be used for scrap parts. We would just pretty much just get rid of it and put a whole new setup in that's already built. That might be faster than trying to like fix it on the robot. But maybe you could fix it on the robot too. I'm not sure. All right, I gotta end the stream for real. All right, peace out.